So I will talk today about robot learning from humans in everyday life scenarios, and as a sub-headline, from robot learning to robot teaching, and I will come to that a bit later. Yeah, and I found it a bit interesting with the talk from Julius yesterday. He wants to remove the human from the loop, and now I give a talk, let's get the human back into the loop. But I hope not in like this tedious data annotation way, but more in an interactive way. So just as a spoiler. Okay, so why robot teaching? And another site reference to yesterday, it's this video that I started with, exactly the same video as Frank, independently of each other. So you already know the video if you've been here yesterday. So that's the PR1. That is tidying up a space, and he does so rather nicely. So it adjusts his magazines, it uses both arms, it adjusts the pillows, the cushions, and later you will even see it use a tool with another object. So that looks all very impressive. And that video is from 2008. And we all know, or if you have worked in robotics, and we all know that we are still very far from that reality. Frank already mentioned it yesterday, that was all teleoperated. So a human operator operated the robot from another room or from the same room, and was able to do all of that. And why am I showing you that video is now that so the humans have all of these capabilities, and the robot is mechanically capable of doing that. So can we learn somehow from those skills of the human? So that's kind of the motivation for robot teaching in the first place. Another example, so that's a bit new, but also already a few years old. So from 2018, where we now don't see teleoperated anymore, but those are actually learned policies. Where the human first teleoperates the robot, and then you learn from those demonstrations. And there have been some very impressive algorithms over the last few years, and you also see here some very detailed motions, like assembling this toy plane or interacting with a cloth, which is a non-rigid object, so it might be shaped a bit differently all the time. But what is often the case in those kind of algorithms is that the demonstrations are actually generated from the experts, often from the same people who programmed the robot, and they are pretty good. And there is much less research. How can we now have naive users that aren't robot programmers provide demonstrations or provide some knowledge to the robot that we can learn from? And there is even less research on, okay, and how does that now influence the human teacher? Because only if those algorithms then result in some policy that the human trusts, and also that the human likes to use the teaching process. So only if the human user sees some benefit in the whole thing, they will keep using it, because otherwise it's just a useless robot and they will stop using it after the first 2 weeks. So yeah, and that's what kind of I'm interested in. How can we make this whole teaching process a bit easier for humans, and how can we design it specifically for humans? Let's continue to the scenario. So yeah, thanks to Pavel for this nice scenario image. So what do we want to do? So let's say we have a room, and there is a big mess, as you see. I mean, that's a crazy mess here. And we would like the robot to tidy up that space. So let's say we go to bed, we have a service robot at home. So that is our vision. Like, we have a service robot at home. We go to bed. During the night, the robot cleans up the whole room. I get up out of bed. Everything is tied up. So for example, we wanted to put the mugs into the shelf or wherever they go, put the ketchup bottle back into the fridge, maybe put another box there, and maybe bring out the trash or whatever. And those kind of things are very different for each household. So each household is very individual, because the mugs, I mean, they will go in the general kitchen area, but they will go in every household into a different cupboard. And also, or the fridge might be located somewhere else, and the maps look very different. So somehow the robot needs to learn that, because it cannot be pre-programmed to know all of that for each household. And the good thing is that we have a human user there. So the human user can actually maybe first tell the robot, okay, the mugs go here, and or maybe even demonstrate, okay, look, that's how you put those specific this specific bowl into the dishwasher or whatever. And yeah, and the flowers are decorations. They should stay there. That's not trash. Don't throw that away. And so similar as if a new roommate moves into you and needs to learn your customs, all the idea is that also you can teach a robot somehow. That's a scenario. We want to tackle some part of that scenario during the iTrust project, so I'm excited for that. And yeah, now we'll tell you a bit more about my previous research that I've done into that general scenario. So first I want to start with a project where we try to do grounded language learning. So I think the colleagues of Prague have some experience with that. So Hala, right? Or yeah. She did a lot of that. So what is the idea of grounded language learning? The idea is, let's say I now want to give the robot a command, like put the ketchup into the fridge. Pretty basic command. But at the beginning, the robot might not know what you mean with those words. So it might not know what object you refer to with ketchup, what location you refer to with fridge, or it might not even know what action you refer to with put. And in grounded language learning, you want to make connections between those words and references in social space and learn that. And so we built a relatively simple system where the robot observes a human, demonstrates some actions, and explaining what they're doing. So for example, here they were just operating a few objects on a table and then explain what they do, and they were pretty free what they want to tell the robot. So for example, here the user might say, I lift the box and I put it over there. And from that, we want to learn something. And we just did that by some statistical co-occurrences. So if the robot detects a specific action with an object and it tries, and specific words occur more often, the words increase in probability. And by that, we learn a lexicon. So the system looks like that. We have camera images and object tracking on the one hand from the robot side, and we also record the speech. We do speech recognition, then identify the actions, segment the speech, align the action into speech chunks, then calculate this normalized pointwise mutual information. I won't go into too much detail, but it's pretty basic. And then if it has learned something and it observes that action again, for example, lift box, it would then, the robot would say that to the user. Yeah, and now my part comes in, or more of my part comes in, where I want to see, okay, how can we make that system a bit better to be used by humans? And one of the big things that influences also the final performance of the system is transparency, and in more detail, the mental model of the user, because you have a mental model how the robot would learn, but that is often very different from how the robot actually learns. So we try to build some extensions to that system, trying to increase the trust in the system, the performance, and the perception of control, because prior research has shown that transparent systems can do that. So the first extension was extension where the robot points at an object and might do so for two purposes. So that's how the pointing might look like. The one purpose is to request the information if it hasn't learned that word yet, or if it has learned the word, then it would communicate that way. Okay, I already know that word. And it is, for example, Pringles or chips or whatever. And that is also a bit similar how what they found in language learning with children, where they also like to point at stuff that they want to know more about. So that's a bit the idea behind that. And the other part was, which is very much not inspired from humans, but because we don't have a display, but the display of the robot could also show then the current system state. For example, here we have the last sentence that was said and the lexicon with some probability. So we wanted to compare that, see how people like that and what were the results on performance and so on. And yeah, what we saw was that transparency was highest in the tablet condition. So the pointing didn't really improve it at all. and we didn't see significant differences for the performance. There were just too many other factors. So for example, you see that it is even worse, the performance is worst for the tablet condition. But we also asked the users what their perceived performance is, and there we see that for the base conditions, the perception of success was much more different from in the other conditions. There they were much more accurate at specifying how good the robot was behaving. There's one more thing. Yeah, again, no significant difference, but you see a slight trend that self-efficacy and perception of control is slightly better for the two extensions. But yeah, we also wanted to did some correlation analysis, and what we saw that knowledge of the system states correlated positively with perceived success of the learning process, and I think I'm saying it wrong. Yeah, and self-efficacy. And so yeah, so that just signalizes us that it's a good thing to look into that, but we haven't succeeded as much as we would hope to. Also because just the system was always a bit brittle, the object detection. I'm happy to talk about it later. Yeah. What we also saw, what I'm not mentioning here now on that slide, is that in some more qualitative analysis, that if the robot was more interactive and started to point, the users also got much more interactive. So they also started to point at stuff and more react to the robot than just this rather passive observer. So that was also interesting and might indicate that a user might use it longer if they also get more interactive. Anyway, so that's that. Next, we also wanted to see if we can learn some movements with Pepper. So we have this cool robot that has very nice looking hands, but it's not really made for grasping or anything. So the SoftBank Robotics even states, okay, that robot is just, the hands are just for gesturing. We wanted to try it anyway. And yeah, so we wanted to have an intuitive system for the robot, for the teacher with a low workload, and we want to learn it end to end. So the idea was that in the end, you get some vision input for the robot, and that generates movements in joint space in that case. So we first built the teleoperation system. You already see me on the right here, where you wear the virtual reality headset. It was the Oculus Rift DK2 back then, and there is also a hand tracker mounted on it. And the robot imitates the user's hand pose, and also the head pose, and also the arm pose was imitated. And you will see in the video how that looks like. And we display the camera view of the robot inside the virtual reality headset. What was very important for me is that in that scenario that you avoid motion sickness, because a lot of people get very sick when they use VR headsets. And the reason for that is, or at least we think the reason for that is the discrepancy between the motion that you perceive and the motion that you see. So if I move very fast, but the robot just follows me slower because it has different limitations, I would vomit immediately. And I'm also very sensitive for that. So we try to build a system that makes it nicer for the user. So we have this virtual screen floating around, and that moves as fast as the robot moves. But we have like a landscape on the background, which gives you this which moves instantly as you move. And that worked pretty well. And yeah, so if you move very fast, you see the mountain move also very fast, and then slowly the display comes into view again as the robot follows your movement. Short demonstration. So what you see here, I think the video is a bit too long for the time we have, but yeah, just the hands being followed, and also both hands, hopefully, if I'm a bit faster. And in the end, there would also be, there's also a short demonstration with the Romeo robot, which unfortunately broke during the time of that. Should I be brave enough to skip? Or no, I just wait now. Yeah, and I might already skip to the next part. So we also then did a user experiment next because we're interested, okay, how does it now actually affect users to use those systems in terms of workload and comfort and so on. So that's the Romeo robot. I just show it because you see it hardly ever anymore, because I think they built like 9 of them and all of them broke probably by now. We still have that in the lab. And the advantage of that one would be in theory that it has 2 additional degrees of freedom in the hand, because Pepper only has the rotation and the Romeo also has pitch and yaw. And it has also stereo camera, so you could also make a stereoscopic view, so you have a bit better 3D perception. User experiment with Pepper, as I already said, so we had 2 tasks, and we wanted to compare kinesthetic guidance with teleoperation. So in kinesthetic guidance, you take the robot arm, you deactivate all the motors, and you move it in the way as you would like. And then we program it in a way that you just touch the display to close the gripper, and then you do it. And every participant did that 5 times. So that's the first trial of that guy. So it takes some time, and they of course have some learning curve, so they get faster with it. So you see, it's not, he's also faster, but it's also sped up. So, but anyway, and that is now the teleoperation system. And you see first in the first trial, the depth perception is a bit off, so he grasped it a bit wrong, but he can correct that and be kind of the feedback loop and see, okay, I need to adjust it in that way, and then put it there. And we also did a second trial, second task where they have to use both hands, so to pour something from a glass in the right arm into the pan in the left arm. So you see that's much nastier to do with kinesthetic guidance, and it might be a bit tricky for teleoperation, but in the end we saw that it worked out nicer than expected, let's say it like that. And yeah, 16 of 21 of the participants preferred actually the teleoperation, and users perceived less overall workload during the teleoperation. And for the pouring task, or the second task, they were significantly faster. For the first task, they were pretty much the same speed for the grasping task. So what we also tried then, okay, can we use that now and learn from that, and learn some policy from that? And I'll just play the video. So that works sometimes. So as I said, the input here is the camera view of the robot, and you already see we attached some additional camera on top, because the camera of Pepper is, especially the depth camera, is not great, to be polite. And yeah, and we also saw, okay, the robot has a lot of problems. So it's really a consumer product and made for gesturing. So it's not very precise. It has a yeah, it just doesn't work as well. So I think that he can still do that one, but it doesn't really generalize to some other locations. So there it would now fail. So we never published that then, because it was just too annoying, and we thought, okay, let's first try to get it to run with a proper robot. So we tried to use it with a KUKA robot arm, and built another teleoperation system without the VR headset, because we thought, okay, that's still like a hassle to put everything on. It's nicer than trying to operate a robot with a mouse and a keyboard, but it's still, can we do it in another way? So here we did it with hand tracking, where the robot follows the tracked hand in Cartesian velocity, Cartesian space, and we tried to train some task, and so that's what the system looks like. So it follows the hand, or in a velocity sense. So if you move to the left, the robot also moves to the left, and so on. And you could perform a task like, so the task we tried to do was just pushing this object over there to that goal. And these are the camera views from top down. So the RGB camera, the depth camera, and we again tried to train an artificial neural network to perform this task with the input, the images, and the output, the robot control. And yeah, so these, you see my colleague pushed it to the front and then to the side. And they learned, were able to learn the policy. It succeeded in many cases. So it succeeded. I think the success rate was not too great. I think it was like 65% in the end. And the problem was that on that side of the table, it almost never succeeded. And it also didn't learn to perform this action where it first pushes it there and then pushes it to the other side. So the policy was only able to learn like this direct movement there. Yeah, so not too great, but we still published it, and yeah, are now in the process of trying to improve the whole system. We also tried, okay, so if we now, can we also do that with dexterous manipulation? So that is now the shadow robotic hand, which has 20 degrees of freedom in the fingers. So very different domain, and we also could also only do it in simulation. And we had two tasks there, or we again used a teleoperation setup to record demonstrations. We had two tasks. That one task was just to reach a certain goal. The other task was to manipulate a cube. And there we tried to combine learning from demonstration with reinforcement learning. And you see it kind of works again. And we saw that for the simple task, the demonstrations of the user actually helped to speed up the reinforcement learning process. But for the more complex task, for this cube task, unfortunately, it didn't work. So because the reinforcement learning worked very well on that task, because it just by random exploration, it reached the goal to move this specific side of the cube to the top very often. But it's the system was hard to just try to operate it in the teleoperation, and it's hard to operate the cube with that system. So we weren't, yeah. So let's move back to the original scenario, to the room, and that is now still research in progress. So where we are wanting to build a new pipeline right now. And so that is what our group mostly works with. It's images and trying to detect object and trying to detect object poses in that image. And Marcus Vince would have told you much more in his presentation about that. But now you have to live with that one slide or two slides. And you see that works pretty well under a lot of different conditions already. So for example, you see the overlaid object model fits very well for the glue or for the water can or for this drill over there. And yeah, for that case, for that approach, we need to know the object model beforehand. However, so that's a different approach where we also try to take object poses. But if you want to grasp the object, you also need to know how to grasp the object. So you need this kind of grasp points or grasp poses. And so for that paper of Dominic Bauer, they hand annotated some grasp poses. And that's of course annoying, and you can't ask a user to do that if they get some new object and to always hand annotate it in simulation. I mean, there are other approaches that also try to learn those grasp poses or just try it in the simulation. But they might be very arbitrary. And objects that we use in every day, they are made for humans and they are made to be usually operated in a certain way. So if you want to actually use the mustard for its dedicated function of dispersing mustard onto my plate, holding it like that wouldn't be a good idea. And that's what a semantic grasp would do. So you want, with a grasp, you want to have some specific function. And for example, also for the power drill that we saw before, everybody knows how to grasp it, but I would first need to learn a robot where to actually grasp it. So again, some colleague of mine have created a system where you use, where you just show the robot, okay, that's how you could grasp it. You use then hand tracking, and you can then translate the hand pose, which looks, our manipulator looks very different than the two-finger manipulator of the Toyota HSR robot that you saw before. But you can translate that grasp pose to the grasp pose of the robot. and then actually perform it. And now I'm again curious, okay, how can we support the user? And one possibility that we'll definitely do and see if it helps the user to teach the robot new grasp poses is to, again, display the grasp pose before and then show it in simulation. And if the user is satisfied, the robot can actually perform the grasp. Or if they are not satisfied, you could redo the grasp, and you could do that with a simple showing in simulation, or even by some kind of simulation. So doing that as a kind of transparency measure. So the proposed pipeline for that is first you do the object pose estimation and verification to get the exact object poses of our beautiful objects on the table. We have a robot query like, oh my God, that PowerPoint messed it up. I'm sorry. Can you show me how to grasp a mustard? You have a human demonstration, you estimate the grasp pose, you give some feedback from the robot, and if it's not satisfactory, you could redo it. And if it's satisfactory, you could actually then apply that grasp and execute it with the robot, plan the trajectory and execute the grasp. So yeah, and that brings me almost to the end of my presentation. I was a bit faster than I thought. So what is my conclusion or my take-home message? So I think there is a big potential in acquiring knowledge from humans, if it's now language or skills or something. And I mean, Frank has shown some very impressive videos yesterday how humans operate objects, and the approach that I've shown are all far away from that. But it would be amazing if we could use that knowledge and have the robot learn from that. And the human teacher is then also a part of the learning loop and influence the final performance substantially. So you can't just assume that you have a perfect oracle who is correct all the time. So we need to have systems that can deal with this uncertainty, with a human that makes mistakes, that has suboptimal demonstrations. And if we build systems that should learn from humans, they need to be able to deal with that kind of dirty information. And also, if we build systems, we need to build systems that users like to use and that they keep using. And I think, and what we have seen in previous research was also that they will only keep using it if they see some added benefit. So if you just, that's a big problem that all of these social robotics companies had, like Cosmo, that had to shut down then. Because people play with it for like a week and then stop using it just because they don't see a real benefit in it. So if we want to have people accept the robots to the daily life, we also need to see how can we build systems that users like to use, that users see a benefit in, and yeah, that's it. Thanks.